from my side. I'm Zitzmann. I'm the general manager of the Canon Automation GmbH, with a 100% daughter company of the association, with the main task to organize the association, to manage it, and to provide all the services that should be provided in terms of the association to the members of the association. So anytime when you want to make use of any CiA automation service, you will get in contact with myself or my team, and we try to assist you in the best way. To start in my topic with the introduction to CiA OpenFD, and I gave you some time to join. Okay, what is CiA OpenFD? Why do we need CiA OpenFD? Well, I think it was in 2012, Bosch presented CAN with flexible data rate. In the meantime, the second generation of CAN-based communication. And the intent was to provide a higher data throughput to CAN-based networks. So the CAN Classic, how we call today the first generation of CAN, has in the meantime propagated to many markets, and to give CAN-based communication and devices based on CAN a certain degree of interoperability and plug-and-play capability, there was a higher layer protocol developed. There were several, but one which is rather famous and today in our main focus, it's the CAN Open protocol. And it was tailored, of course, and adapted to a data link layer as provided by Classic CAN with an 8-byte data field. So, of course, you can now say, okay, I place CAN Open stack on a CAN-FD controller and just run data frames that are not larger than 8 bytes, and everything will work, and it might be a migration path. But if you want to have the full power of CAN-FD, then you should use a software based on your CAN-FD data link layer that can make full use of the benefits and the capabilities of CAN-FD. And therefore, we developed an updated version of CAN Open Classic, the CAN Open FD, which is standardized in CiA 1301 and has now adapted communication objects to allow the full usage of CAN-FD capability. A short reminder, what is the difference in the data link layer? So apparently they are rather the same, CAN-CC and CAN-FD. So they just differ in the size of the certain bit fields, and there the most important point for us is now that we have now a bit field that's capable to carry up to 64 bytes. Pay attention, we can increase from not in the byte-wise granularity this data field, but in certain steps only. And the next thing is, if I like to do so, I can increase the communication speed in the so-called data phase, beginning somewhere in the control field and ending at the end of the CRC field with an accelerated speed. So with a lengthened frame and higher speed, I can increase the data throughput. And the nice thing is I can control both features independently from each other. So if you're communicating in a faster way, then you may know this has impacts on your physical layer. And therefore, if you like to reuse your old CAN topologies that you have designed, for example, for CAN Classic, then you like maybe not to go too fast to avoid any impacts, but on the other hand, you have still the lengthened data field to do certain application-specific things where you would need additional bytes, more bytes than provided in one Classic frame. Yeah, when we are talking about CiA OpenFD, then we are, as we have seen on the first slide, on the higher layers. So we not necessarily care about the physical layer or the data link layer settings. Nevertheless, we have on top of CiA OpenFD some expectations how the lower layers should work. So we give some recommendations how you should implement them. And now as the physical layer design and the data link layer design gets a little bit more tricky in CAN-FD than compared to CAN Classic, we thought, okay, it is wise to provide there some stronger recommendations up to specifications to allow interoperability of CiA OpenFD based devices out of the box. And therefore, we defined not just bit rates, but we defined entire bit timing tables, which result at the end of the day in bit rates, where I said, okay, if you like to make use of the KNFD frames and an accelerated data throughput in the environment of an CAN-OpenFD communication, then we have to support in a CAN-OpenFD device at least these 4 pairs of bit rates. For the nominal bitrate 500 kilobit and 250 kilobit, and they should be combinable in this device with 4 Mbit, 2 Mbit, or 1 Mbit. So maybe via dip switches or whatever. Me as an end user, very simple, can then just select one of these bitrate pairs, and then my device will have the same settings as other devices, as other CAN-OpenFD devices, as they follow the same bit timing. So there are a lot of details to be adjusted, and we encapsulated this that at the end of the day, the use for the system designer, for example, the device user, should be rather simple. Nevertheless, you have to take care a lot also during system design. So therefore, we are on the one hand have already the CiA Series 600 written from a lot of KNFD experts. So they provide some system design recommendations, device design recommendations. And on top of that, we are currently thinking in the IG CAN-OpenFD how we can particularly make use of CAN-OpenFD in topologies or in networks where we are not that keen on high data throughput, but on a lengthened data field, and maybe large topology would avoid high data rates, high communication speeds. And nevertheless, we want to make use of KNFD and CAN-OpenFD, and how you can make this in the best way. We are currently specifying in this CAN-OpenFD group together with lower layer experts. So if you're interested, I'd like to invite you to this group. As written on this last slide, you see here, we have not just these bit rates, those are mandatory, but you have additional bitrate options. We defined there a lot of details so that you can combine a lot of bit rates, and that you can, at the end of the day, have a device being able to communicate in that speed and with that data throughput that is needed in your application. If you need some additional information on the lower layer, so for here it would exceed now the time frame, but there are also in the International CAN conference a lot of talks about lower layer design for CAN-FD, and I would like to point you to CAN Automation's website that you can make here further or discover further interesting information. With regards to CAN-OpenFD, when we started the development of CAN-OpenFD, we tried to keep or to take over a lot of the attributes and the look and feel of CAN-Open Classic. So that's what you know from the document 301. So this means, although it is not depicted that particular in the 301 document, the device model is more or less exactly the same as in 301, what we find now in 301 in the CAN-OpenFD specification. That we have a CAN-Open device residing on a CAN-FD device, having an object dictionary, and having a lot of functionalities like NMT state machine that is operated by the NMT server, that we have an error handler, and so on. Maybe a very small difference is that we have now not only a nominal bitrate, but a data bitrate. We discussed this on the last slides, and that we have a network ID to consider in addition to a node ID. This is in fact not really new, because also for CAN-Open Classic, we have networks IDs in the extension 302, but now we have it in 301, as well as we have some manager functionality or master functionality taken from the 302, also to be considered now in the document, basic document for CAN-OpenFD, so that we can clarify some things like when does a manager device start with its activities and so on. But in general, we try to keep everything identical. In addition to a node ID, we found now a network ID. So this allows us embedding CAN-OpenFD devices rather simple in cloud-based applications. This allows us to communicate rather simple through entire network architectures, as we can simply address, I like now to make a read request to this device in this network and in that node ID. So Mr. Kaploon will show then later on something about this feature that is now inherent in any CanOpen device. State machine, completely identical. The only difference that is really here is that we also try to consider the manager functionality, that we say, when does a device that has a capability to manage a CanOpen network start as functionality? And we consider also a little bit the usage of node ID, network ID, bitrate. We started already in the classic 305 document. When does a device set the node ID, when the bitrate? So this might get visible to the end user depending on the reset command you are using. So therefore, there was a need to clarify it, and we overtook the solution that we had in 305 more or less to CanOpen FD. So you see, a lot of the look and feel of CanOpen Classic remains also in CanOpen FD, still valid. And also when it comes to the services, we were analyzing where do we really benefit from CanFD functionality. And there we saw, okay, in all the network management oriented services like sync message, like the timestamping, like the management of the network management state machine, we just need a couple of data bytes and we are not limited by the CAN classic data frame. So we wouldn't gain too much, but we would change look and feel. So we thought it's wise to keep these services stable. On the other hand, there exist some transport-oriented protocols, in particular the service data object, the process data object. They are really limited in their performance by the size of a CAN classic frame. And if you want to say for diagnostic information, we are also limited somehow by the size of a CAN classic frame. So these three services, the SDO, the PDO, and the emergency service, they needed an update, and for them we provided it. And let's have a short look in the remaining time how we did this update. So for the PDO, it was rather simple. So you know, a PDO works like that you have a mapping table that determines, okay, how many bytes and which ones out of the local object dictionary you like to transfer, and in the receive direction, the same thing. Okay, according to the mapping table, you separate the received data stream and all the pieces you place according to the mapping table to your local object dictionary. And this mapping table has in CanOpen Classic about 64 entries in maximum. So as long as you say, okay, one entry shall not be smaller than 1 byte, then I can fill up a 64-byte CAN FD message. So from that point of view, not really a change was necessary, except the increasement of the threshold value from 8 to 64 byte that I can now map to a PDO. One thing that you should consider, as I've said already, CanFD frames cannot be enlarged in a byte-wise granularity, but only in certain steps. You see them here in this box. And I would recommend not to communicate any rubbish that is currently in the memories when you don't fill up to the next supported frame length. So for example, if you have just 18 bytes, the next one would be 20. So what about with the remaining 2 bytes? Only communicate determined data. So use some padding bytes, fill up to the next supported frame length, and then transfer only meaningful data. And how can we use that? We show this already in the specification 402, where we defined already lengthened PDOs that allow us to control, for example, up to 8 drives via 1 CAN frame. So this helps us in synchronizing activities in one CanOpen FD network. When it comes to the SDO, it's a little bit more complex. So the SDO has already a big function coverage. So we have a read-write access to all data elements. We may have 128 server and client channels. We can even have dynamic SDO cross communication if there is an SDO manager installed in the network, which is available, and my end devices are configurable. We don't have a broadcast transfer. That's a little bit limiting, but there exists a certain tricky workaround to support even that. And we have already a routing capability in CiA 302-7 that allows a remote access and allows more or less embedding entire network systems into cloud-based communication. But there's a big trade-off. So this entire SDO is somehow designed in times that you say, okay, it's typically in a rather static way. There's at the initial system startup, a system designer available who has knowledge in the system, who has knowledge in CAN and CAN Open. He is configuring everything, and then the system is rather stable and running in that way. And we have more and more applications where we have more dynamic requirements that the end user, who is neither a CAN expert nor necessarily a technician, is modifying the system. And this means a lot of the features have to be handled in a dynamic way. And therefore, there was the idea not just to map now the classic SDO to a 64-byte frame, but to modify the SDO to something that we call a universal service data object. It has the full function coverage than the SDO in the classic CAN Open, but in addition to that, it is able to establish dynamic cross communication. It may operate in unicast, multicast, broadcast. It has an inherent routing capability. You may have parallel USDO accesses to the same or different communication partners. So it has a very powerful tool that we added with CAN OpenFD now to this embedded communication. And they are still prepared something in particular. I like to mention this because this might be relevant for Oscar's talk. We have already some possibilities reserved that allow logical addressing. So it is rather easy to extend universal service data communication. Why is it this flexibility? So in contrast to the CAN Open Classic, we have in CAN Open FD the possibility now to determine as a sender the CAN identifier of the frames that are used to carry the request from the client to the server and vice versa from the server to the client. And therefore the destination, who should be the receiver of such a frame, is just coded in the data field. And this means it's very easy for the client to say, okay, now I want to speak to this device, then to that device, then to that device, just by modifying this data byte. And this allows a very dynamic cross communication in the network. So just the sender of the telegram determines the CAN identifier, no longer the server. And therefore, I cannot, as we see it here, just simply say, okay, I want to speak node ID 1, then I want to speak to device node ID 10, and so on. The command specifier says, okay, which type of USDO communication we like to use. We may have several sessions. And then the well-known index and subindex parameters of the object dictionary that is indexed. And we describe now also the data. We get not just something, but we describe the data, and I can map then the application data, and we use the entire frame, the entire CANFD frame, but only if we require it. If we don't require so much data, then we can adapt it to the real needed payload. So due to lack of time, I just browse through the other types of USDO. So we have the segmented transfer, and I think a very simple but very useful transfer is that one, the USDO bulk transfer. So for example, for update of several devices, you just have a short prologue where you negotiate how do we like to do this communication, you clarify some timings, and then you go on and send one segment after the other with the data bytes. And therefore, I can very rapidly update the firmware in a lot of devices at the same time as we support not only unicast, but multicast or even broadcast. And relevant later on also for Oscar's talk might be that one. For all the communication types in the USDO, we have the local version. If I just consider a local network where all are connected to this very same wire, or I can also have the remote USDO. So this is 2 times the very same format. With the long distance routing, I would say, okay, in which network and at there, which node ID I reside, and who is the destination for this information, for this request. So in this way, as long as I have some knowledge about the topology and the network and node ID assignment, I can reach out any device connected to this entire architecture. So we try also to assist system designers by giving more detailed error information. This starts already with the USDOs. Why has a USDO access failed? So it's not just generic error, but we have detailed information so that a system designer has the possibility to say, okay, how to start the countermeasures. And from this, we see how can we benefit. So due to this powerful USDO, for example, we can accelerate the firmware download for several devices as it is depicted here as end-of-line production. Not single SDO access to all the devices, but one broadcast access and it goes. And I have in the meantime the possibility even to open up a second communication and to double check what is the progress of my firmware download. So I save a lot of time and effort during parallel processing and not necessarily because I'm using KNFD. And I can also support dynamic changing systems. So I have here, for example, such a Pedelec, which has an onboard network. And this is a very good example where of an application where the end user is modifying something and you need immediately to set up dynamic communication channels. A host controller who is managing the entire bike needs to have access dynamically to newly attached devices, has to get familiar with them. Are they allowed to act here? And then here he can treat accordingly. Yeah, due to lack of time, I think I skip the emergency. I just show you, we enrich the emergency message by some additional information like time, so that you can bring the emergencies in a chronological order, that you can have an idea about the status of the errors and is it a frequently appearing error. And we clarify where is the error event. If you have very complex devices with several logical devices, then we give you a hint, okay, it's from this or that part of your complex device. And we can have the storage of these errors in a big error history, and we give you some capabilities to browse through this error history, to manage the error history, the type of recording, etc. So you see, a lot of interesting functionality is available now in CanOpenFD. You see here further things that we have added. There, I like to highlight in particular the object 1042, which allows to modify the available payload size. So this might be of interest, for example, for Olaf's talk at the end, that this was added not exclusively, but supporting security options that might be added to CanOpenFD-based systems. Yeah, for CanOpenFD, testing is required. So if you're implementing CanOpenFD devices, then come to Can Automation Office. We are testing them, and then you as a user know, okay, someone has looked on this interface, on this implementation, and the device behaves according to the specification. CanOpenFD is available from several sources. So there are protocol stacks available, there are devices available. The first ones were the I/O modules from several companies. With the drives, I think it's rather easy if you want to have a CanOpenFD, then as many of them are FPGA based, then you might get it with a corresponding stack. The host controllers support often CanFD in the meantime, so you can set up there also a CanOpenFD manager stack and make this host controller operate as CanOpenFD manager. And there, I don't have no current update, but maybe at the end Olaf can say something. So I know they were working on a CanOpenFD gateway. Whether it's now available in a commercial way, I don't know exactly. So much with regard to CanOpenFD. So I think with CanOpenFD, on the one hand, we tried to keep the look and feel of CanOpen Classic. On the other hand, we enriched it by several new functions that I think support system designer a lot. So it makes CanOpenFD meeting the requirements of today's and future networking. And it opens up also the door for further enrichments with regard to cybersecurity, CanOpen safety, and so on. So some work is still to do. So you see here in the lower part of the list what we are currently working on, and it's an ideal moment to step in, to get in touch with the CAN experts, the CanOpen experts, and to bring in your requirements and to assure that also your devices are interoperable in future. So thank you.